This video is designed to help you with word problems related to quadratic equations that you have to solve. These will all factor nicely, so it's not using the quadratic formula, but we're going to take a look at how to set up some of these problems. This first problem is saying that the sum of two numbers is 20, so we'll call those numbers x and y, and we'll not worry about which one is bigger or anything, and we'll just say x plus y equals 20. And it also says that the sum of their squares is 218. So that means x squared plus y squared equals 218. Now, what we're going to do is use our substitution method of converting this equation into y equals 20 minus x by subtracting x from both sides. This allows us to substitute and get an equation into the other equation and get an equation that has only one variable in it. So when we substitute, what we're going to get is x squared plus, and now we're going to square y, but y is 20 minus x. So when we square 20 minus x, we get that. And what we have is now an equation that will be a quadratic in one variable instead of two. And our goal is to solve this. In order to do this, we're going to need to FOIL out that 20 minus x quantity squared term, and then collect things, rearrange, and get everything ready to factor, and do our best to factor it. So this, of course, is going to be x squared plus 400, which is 20 squared, minus 40x, you can verify that for yourself, plus x squared equals 218. Of course, while you're doing this, be very, very careful not to call it 400 plus x squared. Make sure you remember this middle term here when you square a binomial. Don't forget that. The outers and the inners provide you with a middle term. So now our job is to collect these things, and we're going to have 2x squared minus 40x. And after subtracting 218 from both sides and cleaning that up, we'll have plus 182 equals 0. Double check that for yourself. Remember, what we're doing is collecting our x squareds, and then we're subtracting 218 from each side. 400 minus 218 is 182. Our first step then is to factor out the greatest common factor, which will make factoring it easier. So that's going to give us x squared minus 20x plus 91 equaling 0. And so what we're looking for is a way to factor this where 91 breaks up, and they will both have the same sign because it's plus 91. So that means they're both going to be minus. And what we're looking for is two factors of 91 that add up to 20. If you do a little factor tree work, you'll see that two factors of 91 are 7 and 13, and of course they do add up to 20. What this says is x is equal to 7 or x equals 13. Now, since we didn't worry about which one was bigger, and we just called them x and y, what that means is when x is 7, y must of course be 13 to add up to 20. And of course, if x is 13, then y is 7. If we had designated them in some way or known that one was x and the other was the next consecutive integer, for example, then it would be x plus 1. And when we're solving for that one, we're going to get the value of x that is the smaller one. But in this case, we didn't make any distinction between the smallest and the biggest. So let's move on and try a few more problems. Here we have a fairly classic area problem that will produce a quadratic for us, and this one tells us that we have a rectangular pool surrounded by a walk that is 4 meters wide, and it also says the pool is 6 meters longer than it is wide. So let's sketch the pool initially, and that means if we don't know the width, we'll call that x. And we'll call the length x plus 6 since it's 6 meters longer. I'm going to move that x to the inside so that it doesn't get confusing when we put the border around. And then we're going to have a border, which I'll draw in black, that goes all the way around the pool. And the width of it is 4 all the way around. So I'm not drawing the arrows to show that that's the width, but just to let you know that it's 4 all the way around. So what we are also told is that if the total area of the pool and walk is 576 square meters more than the area of the pool, we should be able to find the dimensions of the pool. What that's telling us is that the total area, the area total, equals the area of the pool plus 576. Now, what that really means is that the area of the walkway is 576 square meters. So an alternative way to do this problem would be to break the walkway up into rectangles and just have the rectangles add up to 576 and solve that quadratic equation. You'll get the same equation. But in this case, we should be able to find an expression for the total area. And of course, since it's a rectangle, what that means is we'll multiply the length times the width. Now, of course, the length is x plus 6, but it's also got the length of the total area is x plus 6, but it's got 4 sticking out on each end. So that's x plus 6 plus 8, which is x plus 14. So I'm going to write that as x plus 14. And the total width then is going to be x plus 8 as well. Okay, and that's going to equal the area of the pool, which is x times x plus 6. And that's going to need to add 576 to get the whole total. So now what we've written is an equation that keeps track of the areas of each of these three shapes: the pool's area, the entire rectangle's area, and the knowledge that the walk must be 576 square meters. If we multiply everything out, this should work out fairly routinely. We're going to get x squared plus 14x plus 8x, which is 22x, plus 8 times 14, which is 112. And that's going to equal x squared plus 6x plus 576. Now, of course, our goal is to factor this, but that means we need to use the zero product property, which means we also need to get everything and gather everything on to the same side. Now, the nice thing about this one is when we subtract x squared from each side, the x squareds cancel out, as I've just indicated. And then what we're going to do is get everything on the same side. But let's actually, since it's now a linear equation, sometimes that happens. Let's subtract 6x from both sides. That's going to give us 16x, and then we're going to plus 112 equals 576, and then we're going to subtract 112 from each side, and that's going to get us 16x equals, let's see, 464. Divide both sides by 16, and you're going to get that x equals 29, which means that the original pool is 29 meters by 6 more than that, which is 35 meters. And so those are the dimensions of the original pool. You can check for yourself that if you add 8 to each of those and multiply, you'll get an area that is 576 greater than the product of 29 and 35. So here's another classic rectangular problem, area problem, that's going to produce a quadratic. And this time the x squareds are not going to cancel out, so we'll get a little more drama involved with trying to factor and so forth. This one says it's a rectangular garden surrounded by a walk of uniform width, so it's a very similar kind of problem. So let's draw the garden, and let's draw the rectangular walk of uniform width around it. They're going to give us a different set of information in this case. They're not going to tell us the width of the walk, so we'll just call that x, 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 and x. And they're going to tell us that the dimensions of the garden plus the walk are 16 yards by 24 yards. And that the area of the garden is 180 square yards. So what that means is the entire dimensions of this guy, it's 24 yards this way, and it's 16 yards this way. What that means is we should be able to write an equation once again that's going to allow us, and I'll just label this as the garden, that's going to allow us to find the area of the garden and the width of the, rather the dimensions of the garden and the width of the walk, or anything else that gets asked about. What we know is that the area of the garden is 180 square yards. So if we think about this again, we can simply do the length times the width of the garden if we can write an expression for that. You could also say that the total area minus the area of the walk is the area of the garden. And you could say that the total area minus the garden's area is going to be equal to the, the walkway's area. And you could break the walkway up into rectangles and try to do that. But probably the easiest way to do this one is to simply say, hey, we know the area of the garden. If we can write an expression for the area of the garden, we'll be in good shape. So the width of the garden is then going to be 16 minus 2x. 16 minus 2x, that's going to be the width of the garden. And the length of the garden is going to be 24 minus 2x. And all of that's going to equal 180 square yards, excuse me. So this is, giving us the easiest access to this problem, and sometimes writing these equations and expressions is challenging, but recognize what information they've given you and how to connect it. If you can write an expression for the information they've given you, you're in good shape. Well, 16 times 24 is 384, which I've calculated off to the side, minus 48x, that's the inners, minus 32x, that's the outers, and plus 4x squared, don't forget the square in this case, and that's going to all equal 180. Let's put this in proper order. That's going to give us 4x squared minus 80x plus 384, but minus 180 from each side, so that's going to be plus 204 equals 0. We factor out the greatest common factor, which is 4. That's going to give us x squared minus 20x plus 51. That makes life a lot easier because now we have the following, and we're looking for two factors of 51 that add up to 20. And we find that 51 factors only into 3 and 17, and fortunately they add up to 20. So we get 3 and 17. What that means is the width of the walk, is 3 yards according to the math, or 17 yards according to the math. Now, of course, 17 yards is too big. It wouldn't be possible to have a total width of 16 yards, nor a total length of 24 with 2 x's added onto each side. So we can conclude that the walkway is 3 yards wide. Let's try one more equation. It's a classic rocket kind of problem. Here we have a fairly classic thrown or projectile motion problem. Oftentimes these are rockets or a thrown object, and it leaves either the ground or some stand or building or tower from a certain height. If it's projected upward, then it has some initial velocity. And so let's make a quick sketch of what we're looking at here. What we have is a building above the ground, and our object is thrown up off the building and reaches some peak height and then comes down and reaches the ground. So This is the path of the object, and we'll put a little arrow on it just to identify what's going on. And we're looking for this time right there when the object hits the ground. So these kinds of problems, if this one is done in feet, with feet per second and an 80-foot building, so what that tells us, we have height as a function of time, and when it's feet per second, what you're going to get, the acceleration of gravity produces this equation. If it's meters per second, that's going to be negative 4.9 meters per t squared. Those are the way the numbers work out due to the force of gravity. And it's negative 16 t squared. And that is, as I said, due to the acceleration of gravity. And if there were no gravity, then that term would not be there. So if you were doing this in space, for example, with no gravity, or were no perceptible gravity, then that term wouldn't be there. Then what's going to happen is there's a component that says r sub I, or initial upward velocity, times time. Of course, it could be an initial downward velocity, but in this case, it's an initial upward velocity. And that has a component that gets multiplied by the time, because it's always striving to go at that speed. So for example, if we were doing this in space with no perceptible gravity, the height of the ball would just continue upward at that constant velocity, and so you'd multiply 64 feet per second by however many seconds it was going for. So the gravity and the upward initial velocity of this thing are fighting each other. And what we also have is h sub I, which is the initial upward the initial starting height. In this case, it's actually starting at 80 feet above the ground. So we're going to write that in, and just to remind ourselves, so it's 80 feet. And so if we fill in all this information, what we're going to get is that the height at any given time is negative 16 t squared plus, in this case, 64t plus 80. Now what that really means is if you plugged in t being, let's say, 3 seconds, you would find what the height of that object would be at after 3 seconds of 3 seconds after it was thrown upward from the top of the building. So this is the height at any given time, and it's a nice sort of physics formula that you'll see a lot of in high school. What they're asking here is, when will the object hit the ground? So this is all assuming this height at any given time is actually relative to the ground, because we're starting at 80 feet up. So what we're really asking is, when is h of t 0? So what we're trying to do is solve for when h of t is 0, which means we plug in 0 for h of t, and we look to find what value of t makes this true. So in other words, we need to solve a quadratic. So our first step is going to be to factor out the greatest common factor, which in this case is negative 16. And we want to do negative 16 just to get the signs a lot easier to deal with. We would like our first term to always have positive coefficient, and in this case positive 1 is even easier. That's going to leave us with negative 4t and negative 5. So be very, very careful with those signs. If you distribute negative 16 back out, you'll see we get what we started with. Alternatively, you could add 16t squared to both sides, subtract 64t from both sides, subtract 80 from both sides, leaving 0 on the right and everything else on the left with opposite signs, and you would get essentially this equation. Now, it's much easier just to factor out negative 16 as long as you get your signs right. Then what we're looking for is the way to factor this. So we're going to get t and t, and of course this one factors easily. We need 5 and 1, and they're fighting each other, and we want the bigger one to be negative, so it's negative 5 and plus 1. And what that means is t equals 5 seconds, it will hit the ground. Now arguably, solving this equation, it also says t equals negative 1 second. Now, what does that mean? So the clear point is that at 5 seconds, this ball has hit the ground. And if you dug a big hole where the ground is and just let it keep plummeting, you could calculate, how long it would take for it to be, 1,000 feet down or whatever. And so you'd put negative 1,000 in and you'd have something else to solve. But what does that t equals negative 1 second mean? What it means is that we would have had the equivalent flight path for this as if a rocket had been launched 1 second earlier from the ground. So you notice I've kind of traced in the path there. If the launch of the rocket 1 second earlier, before it was thrown up, had been launched at a higher speed so that it reached the top of this 80-foot building while it was still with a velocity of 64 feet per second, then it would follow the exact same path that it's followed after, as from this problem. But beforehand, it would have been launched 1 second earlier. Now, of course, the upward speed must have been, upward initial velocity must have been faster than 64 feet per second in order to be still going 64 feet per second at the top of the building as it leaves the building. So you can imagine throwing it at time t equals 0, at 64 feet per second on an upward velocity from the top of the building, or the equivalent flight would be launching a rocket or launching the object from the ground level 1 second earlier, but at a higher speed so that it just hit the top of this building at 64, still going 64 feet per second. That's possible to calculate, but more than we need to do here. I hope this has helped. And of course, this means that the answer t minus 1 equals negative 1 second can be tossed out, and t equals 5 seconds is the answer to our question when the object will hit the ground.